Good morning, students. In the previous class, that is class 1 of the chapter Coordination Compound, already covered the introduction part. What is a simple salt, normal salt, double salt? What is a complex salt or complex compound? What is the difference between double salt and complex salt? What is the ligands? Types of ligands? That is cationic ligand, anionic ligand, neutral ligand on the basing upon the charge. And on the basing upon the donor side, the number of donor atom, ligands are monodental ligands or ambidental ligands, bidental ligands. It is of two types, symmetrical bidental and unsymmetrical bidental, polydental ligand, ambidental ligand, chelating ligand, bridging ligand. These are the types of ligand. Next, what is coordination number? What is oxidation number? How to calculate the coordination number and oxidation number for a central metal atom or ion? Then, what are the IUPAC rules for giving the name, systematic way of giving the name for a complex one? Already we discussed giving the name of three type of complex. One is cationic complex, one is anionic complex, and one is non-ionic or neutral complex. Today, there is a class 2 for the chapter Coordination Compound. I will try to complete. If name is there, how we write the structure, the formula? Next, Orinore's theory, the father of coordination chemistry, W.F. Orinore, gave a theory according to him, his name known as Orinore's theory. And the last one is valency bond theory. So before going to the today class, let us recap. That is, again we write the structure and its name according to IUPAC system. Now we cover 3 to 4 types. One is a cationic complex, one is an anionic complex, one is a non-ionic complex, and the last one is both cationic and anionic complex, where both cation and anion both are complex part. Let us discuss one by one. Mark that. Between LiAlH4 between CONH3 5 BrSO4 third type NiCO4 fourth one CONH3 6 CrCl6. Let us try to give the name of the following complex. This one is the complex part is anion, so it is known as anionic complex. The cation part of this complex is the complex, so it is known as cationic complex. It is neutral complex, non-ionic complex. And last one is cation part is complex, anion part is complex. Let us write their name one by one. So first one is, so the most important point is there, whether it is a cationic complex or anionic complex or neutral complex, name of the cation first followed by the anion. So its name. And another one important point is name is always small letter. So its name is lithium, then space, tetra, hydrido, aluminate. So we have to write now the oxidation number of central metal atom, that is aluminium. Lithium is +1, it is not known, that is X. 4 into -1 is equal to 0. Implies X minus 3 is equal to 0. Implies X is equal to +3. That is I. Lithium, tetra, hydrido, aluminate 3. Because it is the anionic part is the complex one. If complex part is the anion one, then metal atom we have to write its if Latin name is there along with ADE. Next this one, complex part is the cation. So first we write the name of the ligands. After writing the name of ligands, then central metal atom. So it is pentaamine, bromido, cobalt, bracket, sulfate. We have to write the oxidation number. It is not known, let it is X. 5 into neutral 0 plus minus 1 plus minus 2 is equal to 0. On solving, X is equal to plus 3. So I. So its name is pentaamine, bromido, cobalt 3, sulfate. Next is third one, neutral one. If a complex is a neutral one, then first we write the name of the ligands followed by the central metal atom. 4 is there. So tetra, carbonyl, nickel. Within bracket we have to write oxidation number. It is not known. Let it X. 4 into neutral ligand 0 implies X is equal to 0. So its name is tetra carbonyl nickel 0. Next is about the fourth one, where cation part is complex, anion part is complex. So we have to write the first part, cation part, then we write the anionic part. So its name is hexaamine, cobalt, bracket, we write the oxidation number. Next, hexa, chlorido, chromate, oxidation number. We have to find out the central metal atom oxidation number not known, let it is X, plus 6 into neutral 0 plus X plus 6 into minus 1 is equal to 0. 2x is equal to plus 6 implies X is equal to plus 3. So it is I. So its name is hexaamino cobalt 3, hexachlorido chromate 3. These are some extra example for giving the IPAC name of a complex whose formula is given. Now today we start that name is given, how we write its formula. Let us discuss one by one. First one, for example, first one, diamine silver 1 chloride. Second one, tetra carbonyl nickel 0. Next one, hexa aqua chromium 3 chloride. Mark that. Let us write their formula one by one. 2 to 3 steps are there. First one is, whether it is a cationic complex or anionic complex, first we write cation followed by anion. Next, inside the coordination sphere, first we write the central metal atom followed by the ligands. Next point, if more than one ligands are there, irrespective of their nature and charge, we write them in alphabetical order. And the last one is, while writing the formula of a complex, one point is taken into account that the total charge on the cation must be equal to the total charge on the anion. Let us verify first. Mark that it is diamine silver 1 chloride. Answer bit 1. diamine silver 1 chloride. It is clear that complex is the cationic part. So cation part is the complex, next chloride is here. So after the square bracket we have to write the central metal ion, that is silver, Ag. Diamine NS3 present 2 times. As it is a cation, it is a plus X, it is a minus 1. As it is a cation, it is a plus. What is the charge? It is not known. Let it is X. We have to find out the X. Mark that. And the oxidation number is 1 is given. So it is plus 1 plus 2 whole into neutral is equal to plus X. Implies X is equal to plus 1. So it is plus 1. Plus 1 minus 1 cancel. So the expected formula is NS3 whole twice Ag NS3 whole twice Cl. It is diamine silver 1 chloride. Move to the second part. What is the second part? That is tetracarbonyl nickel 0. It is clear that it is a non-ionic complex. So inside the square bracket we have to write the metal atom that is known as nickel, and 4 carbonyl is there, so you have to write CO4. As it is the oxidation number is 0, metal atom, so 0 plus 4 into 0 is equal to 0. So no charge is there on the complex, so it is clear that it is a neutral complex. Move to the next one. What is the next one? Hexa aqua chromium 3 chloride. It indicates that complex part is cation. So cation is in complex part cation, Cl is anion part. So inside the square bracket, first we have to write the central metal atom, that is chromium. Then aqua, water is there, 6 times, so Cr6. As it is a cation oxidation, now we have to find out it is minus 1, it is a plus X. Our aim is to calculate what is the value of plus X. Mark that it is given 3. So 3 plus 6 into 0 is equal to plus X. Implies that X is equal to plus 3. Now it is a plus 3. So 3X, in place of X we write 3. So 3 moves to this one, 1 moves to this side. So the formula is CrH2O whole 6, Cr3. Its formula is, the name is hexa aqua chromium 3 chloride. Let us discuss another one is there. Potassium hexacyanido, potassium hexacyanido ferrate 3. Mark that. From this name it is clear that it is the cation simple and anion part is the complex. So we write K and it is the square bracket, it is a plus 1, it is not a known, let it is a minus X. And inside the square bracket first we write iron as is the anionic part. So in anionic part the name is moved to the Latin name along with ATE. So we write iron Fe. Hexacyanido means cyanide appears 6 times. Then we have to find out what is X. Mark that it is given that is plus 3 plus 6 into minus 1 is equal to minus X. Implies that X is equal to 3. So by writing 3 moves to this side, 1 moves to this side. The expected formula is K3 Fe CN6. It is the formula for potassium hexacyanido ferrate 3. It is all about the formula is there, then you write the structure. Structure is there, then write the formula. Next switch over to isomerism. Next, focus to structural isomerism. Structural isomerism. What do you mean by structural isomerism? When the same molecular formula for a complex but they are arranged differently, then it is known as structural isomer, and each one is known as other structural isomer, and the phenomenon is known as structural isomerism. Generally, structural isomerism again classified in 3 to 4 types. That is ionization isomerism, linkage isomerism, hydrate isomerism or solvent isomerism, and last one is coordination isomerism. Let us discuss one by one. First one is ionization isomerism. Second one, linkage isomerism. Third one, hydrate solvent or hydrate isomerism. And fourth one, coordination isomerism. Each bit belongs to carry 2 marks. The definition along with one example is a 2 mark question. Let us discuss one by one. First one is ionization isomerism. What do you mean by ionization isomerism? When the same molecular formula represent 2 or more structure, when the same molecular formula represent 2 or more structure which liberate different ion in aqueous solution. I repeat again. When the same molecular formula represent 2 or more different structure which liberate different ion in aqueous solution, then one is known as others ionization isomer, and the isomerism is known as ionization isomerism. Mainly it differ in liberating different ion in aqueous solution. For example, mark that. Mark that. I read 2 structure. Its name is pentaamine bromido cobalt 3 sulfate. I rewrite its name. Mark that. Its name is pentaamine bromido cobalt 3 sulfate. Mark that. When it ionizes, it liberates sulfate ion. While this complex name is pentaamine sulfato cobalt 3 bromide. Its name is pentaamine sulfato cobalt 3 bromide. When it ionizes, it is the ionized part. When it ionizes, it liberates a bromide ion. Mark that. Same formula, but the first one liberates sulfate ion, while the second one liberates a bromide ion. So the on ionization gives different ion in aqueous solution. So this one is known as its ionization isomer, and the phenomenon is known as ionization isomerism. Move to the second one, that is linkage isomerism. Second one, linkage isomerism. What do you mean by linkage isomerism? Same definition, similar definition. When the same molecular formula represent two or more structure which differ in attachment of the ligand with the central metal atom. I repeat again. When the same molecular formula represent two or more structure which differ in linking attachment of ligand with the central metal atom, then one structure is known as linkage isomers of other and the phenomenon is known as linkage isomerism. The most important thing that in this type of complex there must be one ambidentate ligand. Because of definition we know ambidentate ligand is the differ in the point of attachment of the donor atom with the central metal atom. For example, mark that Cr NH3 5 NO2 Cl3 and another one Cr NH3 5 ONO Cl3. Mark that same molecular formula is there, different structure. Its name is penta amine nitrito N chromium 3 chloride, while its name is penta amine nitrito O chromium 3 chloride. Mark that. What is the difference? There is the presence of the ambidentate ligand. What is the ambidentate ligand? That is that ligand having two donor sites, but at a time one of them linkage donate to central metal ion with lone pair of electron. Here the donor atom is nitrogen, linking atom is nitrogen, while the donor atom or linking atom is oxygen. If donor atom is nitrogen, then it is known as nitrito N. If donor atom is oxygen, it is known as nitrito O. So each one is known as others linkage isomers and the phenomenon is known as linkage isomerism. I repeat again. What do we mean linkage isomerism? That is same formula represent two or more structure which differ in attachment, linking of a donor atom with the central metal atom. Next one is hydrate isomerism or solvent isomerism. Move to the third one, that is hydrate isomerism. Third one, hydrate isomerism. What do you mean by hydrate isomerism? When the same molecular formula represent two or more structure, when the same molecular formula represent two or more structure which differ in the number of water molecule that is present inside the coordination sphere behave as a ligand. I repeat again. When the same molecular formula represent two or more structure in which there is the number of water molecule is different which is present inside the coordination sphere behave as a ligand. That is, number of ligand water molecule is differ in each other structure. Then one is known as others hydrate isomer and the phenomenon is known as hydrate isomerism. Let us mark that. Bit 1 Cr H2O6 Cl3, bit 2 Cr H2O5 Cl Cl2 dot H2O, bit 3 Cr H2O4 Cl2 Cl dot 2H2O. Mark that same formula represent three structure. Here number of water molecule acting as ligand is 6. Here number of water molecule acting as ligand is 5. Here number of water molecule behave as ligand is 4. So same formula but differing number of water molecule acting as a ligand. So what is its name? Its name is hexa aqua chromium 3 chloride. Its name is penta aqua chlorido chromium 3 chloride monohydrate. Its name is tetra aqua dichlorido chromium 3 chloride dihydrate. Mark that same formula, differing number of water molecule acting as ligand. The first name is hexa aqua chromium 3 chloride. The second name is penta aqua chlorido chromium 3 chloride monohydrate. Third one is tetra aqua dichlorido chromium 3 chloride dihydrate. In first case, the number of water molecule behave as ligand is 6. In second case 5. In third case is 4. Each one is known as others hydrate isomers and the phenomenon is known as hydrate isomerism. Move to the last one, that is coordination isomerism. Move to the last one. The last isomerism is, that is known as coordination isomerism. Fourth one, coordination isomerism. What is coordination isomerism? When the same molecular formula represents two or more structure in which there is an exchange of cationic part and anionic part, in which there is a difference in ligand present in the cationic part and anionic part. In this case, in this complex, cation part and anion part both are complex, in which differ in the presence of either central metal atom and also presence in the ligand. For example, mark that CrH2O6, COCl6, and second one is CrNS36, CrCN6. Mark that. Let us discuss one by one. So first one, it is the cationic part, it is the anionic part, both are complex one. Then we have to follow the IPSC rule for the complex cation and for the complex anion. So what is its name? Its name is, mark that, hexa aqua chromium, hexa aqua chromium bracket hexa chlorido cobaltate bracket. It is oxidation number. We have to calculate the oxidation number, that is, it is not known, let it be x. 6 into 0 plus x, 6 into minus 1 is equal to 0, implies 2x is equal to 6, give rise to x is equal to plus 3. That is, mark that. One name is hexa aqua chromium 3 and hexa chlorido cobaltate 3. With the same formula we change the isomer. Mark that. Same formula. Its isomer is COH2O6 CrCl6. Its isomer is this one and its name is hexa aqua cobalt bracket hexa chlorido chromate bracket. We have to find out that it is x plus 6 into 0 plus x 6 into minus 1 is equal to 0. On solving, x is equal to plus 3. So its name is hexa aqua cobalt 3 hexa chlorido chromate 3. Mark that same formula but different. Exchange their coordination sphere, exchange their central metal atom, exchange their ligand in cationic and anionic complex. Move to the second example. Another one example is there. Mark that. Here is its isomer is Cr that is CO NH36 CrCN6. Mark that its name is hexa amine chromium 3 hexa cyanido cobaltate 3 and its name is hexa amine cobalt 3 hexa cyanido chromate 3. These are some examples of coordination isomer. Each one is known as other coordination isomer and the phenomenon is known as coordination isomerism. It is all about the structural isomerism. Next we switch over to Ordination theory. The father of coordination chemistry, W.F. Ordiner, give a theory according to him that is known as Ordination theory. This is 3 marked. What is the question? Write short notes on Ordination theory. Next we discuss Ordination theory for complex compound. 4 to 5 points are there, postulates under this theory. Let us discuss one by one. Point 1. In every complex, central metal atom exhibit 2 types of valency. I repeat again. In every complex, central metal atom exhibit 2 types of valency. That is, one is known as a primary valency and another one is known as a secondary valency. Every central metal atom in a complex exhibit 2 types of valency. One is known as a primary valency, while another is known as a secondary valency. Point 2. Primary valency is known as ionizable valency, while secondary valency is non-ionizable valency. I repeat again, second point. Primary valency is the ionizable valency, while secondary valency is non-ionizable valency. Point 3. Primary valency corresponds to the oxidation number, while secondary valency corresponds to the coordination number. I repeat again, third point. Primary valency corresponds to the oxidation number, while secondary valency corresponds to the coordination number. Next point. Primary valency is shown by the metal in the formation of simple salt, while secondary valency is shown by the metal in the formation of a complex. I repeat again. Primary valency is shown by the metal atom in the formation of a simple salt, while secondary valency is shown by the metal atom in the formation of a complex. Next point. Every metal atom try to maintain its primary valency and also secondary valency. I repeat again. In a complex, every metal atom try to maintain its primary and secondary valency. Next point. Primary valency is satisfied by the negative ion, while secondary valency is satisfied by negative ion as well as a neutral molecule. I repeat again. Primary valency is satisfied by the negative ion, while secondary valency is satisfied by negative ion as well as a neutral molecule which behaves as a ligand. Next point. Primary valency is a non-directional nature while secondary valency is a directional nature. I repeat again. Primary valency is non-directional nature while secondary valency is a directional nature. Next one. The geometry of a complex is decided by the secondary valency. As the secondary valency is a directional one, so it decides the geometry of a complex. For example, if a secondary valency is 4, coordination number is 4, expected geometry of a complex is either tetrahedral or square planar. I repeat again. The secondary valency, that is coordination number, decides the geometry of a complex. It may be coordination number 4 or maybe coordination number 6. If coordination number is 4, expected geometry is either tetrahedral or square planar. On the other hand, if coordination number is 6, the expected geometry is octahedral. While drawing a structure, primary valency represented by dotted line, while secondary valency represented by straight line. And the most important point, in every complex, the central metal atom try to maintain its secondary valence. These are the postulates of Orino's theory. So in order to obey this theory, Orino gave a cobalt-amine complex to illustrate how the different complex satisfy its secondary valency, that is a coordination number. Let us discuss by taking a cobalt-amine complex. Mark that. CO NS3 6Cl3, first complex. Here, while drawing a structure, the primary valency represented by the dotted line, broken line, while the secondary valency represented by straight line or solid line. Mark that. CO 1, 2, 3, 4, 5, 6. 1, 2, 3. Cl NS3, 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 NS3. Here, primary valency 3, secondary valency. Primary valency known as oxidation number, while secondary valency known as coordination number. It is structure 1. Next, second structure CONS3 5 Cl2, structure 2. Here primary valency +2, secondary valency 6. CO 1, 2, 3, 4, 5, 6. Cl, NS3, 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 NS3. Third one, CONS3, 4 Cl2, Cl. That is third structure. Primary valency +1, secondary valency 6. 1, 2, 3, 4, 5, 6. NS3, NS3, NS3. Mark that in the structure here 6 ammonia molecule behave as the coordination number representing secondary valency by 6 solid line, while 3 chlorine atom which is present around the ionizable part represent the oxidation number which is ionizable part represent the 3 dotted line. 1, 2, 3 dotted line. But here what happened? Mark that one of the negative ligand behave a dual role, satisfying both its primary valency as well as secondary valency. So 2 dotted line is there, 1 dotted line, 1 straight line is here. Similarly, here 2 chlorine atom behave a dual role, satisfying the primary valency as well as the secondary valency. So 2 dotted line, 1 dotted line, 1 straight line for 2 chlorine atom is there. So in each the structure, it is clear that in a cobalt amine complex, in any complex of a metal atom, here the secondary valency always try to fix. It is all about the Arrhenius theory. Next, switch over to next theory, that is valency bond theory. It is a very, very important one for the chapter coordination compound. Let us discuss the various postulates of valency bond theory. Next one is valency bond theory. Very, very important one. What are the postulates? The various postulates of this theory are point by point. Point 1. In a complex, every complex, the ligands try to donate at least a pair of electrons to the central metal atom. I repeat again, the point 1. In every complex, the ligand try to donate pair of electron, at least one pair of electron to the central metal atom. Point 2. In a complex, every central metal atom or ion accommodate the electrons donated by the ligands is equal to its coordination number. I repeat again. The central metal atom or ion has the capacity to accommodate ligand electrons is equal to its coordination number. Point 3. In a complex, every ligand possesses at least one sigma orbital having a lone pair of electrons. I repeat again. In every complex each ligand possesses at least one sigma orbital containing a lone pair of electrons. Next point. While accommodating ligand electron, central metal atom may use its hybrid orbital involving s orbital, p orbital as well as d orbitals. I repeat again. In order to accommodate the ligand electron, the central metal atom uses its hybrid orbital s orbital, p orbital and d orbital for accommodating ligand electrons. Next point. The vacant hybrid orbital of the central metal atom overlap with the filled sigma orbital of the ligand, forming ligand metal sigma bond. I repeat again. The vacant hybrid orbital of the central metal atom overlap with the filled sigma orbital of the ligand, forming a ligand metal sigma bond. Next point. During the hybridization, the central metal atom uses either inner n-1 d orbital or outer nd orbitals. I repeat again. For accommodation, The central metal atom uses hybrid orbital of inner n-1d orbital or outer nd orbitals for hybridization. I repeat again. For hybridization, the central metal atom may be used the inner orbital, that is n-1d orbital, or outer orbital, that is known as nd orbitals. Next point. If the central metal atom use inner n-1d orbital, then that type of complex is known as inner orbital complex or low spin complex or spin paradox complex. I repeat again. During the hybridization, if central metal atom use n-1d, that is inner d orbital, then that type of complex is known as inner orbital complex or low spin complex or spin paired complex. Maximum chances is that it is formed diamagnetic in nature. The complex possesses diamagnetic nature. On the other hand, if the central metal atom uses outer d orbital, that is nd orbital, then it is known as outer orbital complex or high spin complex, or it is known as spin free complex. I repeat again. If the central metal atom uses outer nd orbitals, then it is known as outer orbital complex or high spin complex or spin free complex. Maximum chances that complex is paramagnetic nature. Next point. During the filling of the electrons, there everywhere Horn's rule is applicable. Next point. While filling the electron, if unpaired electron is there, give rise to the paramagnetism. That complex behave like paramagnetic nature. And the paramagnetic character depends upon the unpaired electron, and it is calculated by a character that is known as mu. A formula is there for calculating paramagnetism or paramagnetic character of a complex. That formula is known as mu is equal to n whole into n plus 2 whole root over bm, where mu is known as a parameter to calculate the paramagnetic character, and n is known as number of unpaired electron, and bm is known as Bohr magneton, that is the unit of magnetic moment. That means higher is the number of unpaired electron, higher is the magnetic moment mu, indicates that higher is the paramagnetic character. And the last point, the most important point, that means in presence of a strong field ligand, the unpaired electron may get paired off. I repeat again, the last point, the most important point. In presence of a strong field ligand, the unpaired electron may get paired off, defeating the Horn's rule. Let us discuss some complex, how this formula is applicable. So we discuss mainly focus to two type of complex. One is C.N6, that is octahedral complex, and one is C.N4, that is square planar or tetrahedral complex. Again, in octahedral complex is of two types, that is inner orbital complex and one is outer orbital complex. That means if the central metal atom uses n-1 into d orbital, inner d orbital, resulting in the formation of inner orbital complex. On the other hand, if the central metal atom uses outer d orbital, that is nd orbital, resulting in the formation of outer orbital complex. Let us discuss one by one. First is inner orbital complex. First we discuss octahedral complex. Octahedral complexes means coordination number is equal to 6. It has a two subheading. Subheading A, that is inner orbital complex. We choose one suitable example. FeCN6 4 minus complex ion. Let us discuss this one. That means a complex. What is the formula? Formula is known as FeCN6 4 minus complex ion. Let us discuss how this point postulates apply to here. So from this formula it is clear that the central metal ion is Fe, where from this it is clear that it is known as the oxidation state is 2. Atomic number, that is known as 26. If we go through the noble gas electronic configuration, for S2 3d6, mark that. If we go through the out, it is known as 3d, 4s, 4p. Now it is 6, 1, 2, 3, 4, 5, 6 for S2. So if we calculate 0.2, if we calculate the oxidation number, it is X plus 6 into minus 1 is equal to minus 4, indicate that X is equal to plus 2. So iron now it is in plus 2 oxidation state. That means it loses 2 electron. That means its structure, that is 3d6. Mark that, it is 3d, 4s, 4p, 1, 2, 3, 4, 5, 6. Mark that. Point 3. We know that it is a strong field ligand. So one point is there, in presence of a strong field ligand, the unpaired electron get paired off. So what happened? This one paired off, making 2 vacant 3d orbitals. So 6 ligand is there, that is third one is FeCN6 4 minus ion. So what do we observe here? Donate pair of electron. So 2 type of symbol is there, mark that. This one for metal atom electron, it is for ligand electron. So from this it is clear that 2 3d orbital, 1 s orbital and 3 p orbital, 4 p orbital get hybridized, resulting the formation of D2sp3 hybridization. As here n-1 d orbital involved, it is known as inner orbital complex. So from this diagram it is clear that since all the electrons, all the orbital get paired off, that means n number of unpaired electron is 0, therefore this complex is diamond in nature. And since the coordination number is 6, it is an octahedral complex, inner orbital complex, low spin complex, because spinning is nearly 0, no unpaired electron. So it is an octahedral complex, or as it is n-1 d orbital involved in bond formation in hybridization, so it is known as inner orbital complex, low spin complex, and as there is absence of unpaired electron, it is magnetic character is diamagnetic, and the expected hybridization is D2sp3 hybridization.